Hoover High School Honors Chemistry. This is Lesson 7. It's on ionic bonds. So the 90 natural elements on the periodic table combine to form millions and millions of compounds. Maybe as many as 50 million. I don't know. I've read various numbers, but it's well into the tens and tens of millions of compounds out of just 90 elements. So chemical bonds are central to chemistry because they are how atoms are joined to create new compounds. Even so, there are only 3 ways elements can combine. So first, ionic bonds. An atom passes electrons to another atom. Second, covalent bonds. That's where atoms share electrons. And third are metallic bonds. In this case, electrons jump from one atom to another, so atom to atom, like frogs on lily pads. They just kind of jump around in between atoms almost kind of freely, and this creates a chemical bond between metal atoms. So the amazing thing is there's only 90 elements in the entire universe, and the way they create all these tens of millions of different substances is by connecting in only 3 different ways. And in the next week, you're going to learn all 3 of these ways. So the Octet Rule says that atoms are in the most energetically favorable state when they can fill their valence orbital. Octet means 8. It's called octet because all elements need 8 electrons to fill their valence outer orbital. The exceptions are hydrogen and helium, which can hold 2 electrons in their valence orbitals. So noble gases such as helium and neon at the end of each row already have full valence orbitals. They're called noble because they are like royalty. Other elements want to be like them. Other elements want to fill their valence orbitals. And so they want to be like a noble gas. So that's why they're called noble gases, because noble gases were born with a full octet. So they're perfectly happy the way they are. So all atoms want to be like a noble gas and have a full valence orbital. So let's look at lithium. Lithium has 3 protons, 4 neutrons, and it has 3 electrons, and one of those is a valence electron in that second orbital. So how could lithium fill its valence orbital? Well, if it wants to get 8 electrons in the second orbital, it could add 7 electrons, and that would give it a full second orbital, and it would look like neon. We say that lithium in that case would have the electron configuration of neon. It wouldn't become neon because it doesn't have the same number of protons, but it looks like it. It has 2 electrons in the first orbital and 8 in the second. So it would have the electron configuration of neon, so it would be like that noble gas. But that's almost impossible. In fact, it's absolutely impossible. Lithium, if you remember, we talked about electronegativity, has a very low electronegativity. Everything over on the left side of the periodic table does. That means it would have a very difficult time pulling in even 1 electron, let alone 7 electrons. In fact, lithium never does pull in electrons. It just never does it in the real world. So there's no way lithium is going to be able to fill its second orbital by adding 7 more electrons to give it 8. So what's another way it could do it? Well, so there we go. That's not going to happen. Lithium becoming like neon by adding 7 more electrons. So what's another way it could do it? Well, there's kind of a sneaky way it can do it. Or lithium can lose its second orbital electron and have a full first orbital like helium. So now we see the arrow is pointing from lithium over to helium. In other words, it goes backwards. Lithium goes backwards to the nearest element, nearest noble gas, which is in the first row, and that's helium. So you see that the second orbital electron disappeared, and effectively so did the second orbital if there's no electron there. Didn't really disappear, but there's no electrons in it. So now lithium only has 1 orbital, the first orbital. It has 2 electrons, which is a full valence orbital for the first orbital. It's all it can hold. And so now lithium has a full valence orbital. So it was kind of a backwards way of doing it, but it worked. Now, will lithium give away an electron like that? Yes, absolutely. It has a very low ionization energy. Remember, all the elements over on the left side of the periodic table have low ionization energies. That means it's very easy for lithium to give away that electron. Why does it give it away? Because some other atom came and pulled it away from lithium. So it didn't take very much energy to pull that second orbital electron away from lithium, so it gave up that electron, and now it has a full valence orbital being its first orbital. So lithium is now like a noble gas. It's like the noble gas helium. Conclusion: the easiest way for lithium to be like a noble gas is to lose one electron and have a full first orbital like helium. Okay, let's take a look at fluorine on the other side. That's the second element from the end of the second row, right next to neon. So all atoms want to be like a noble gas and have a full valence orbital. So if you look at the electron diagram of fluorine, you see that its second orbital has 7 electrons. All it needs is one more electron to fill that empty space there, and it will have the electron configuration of neon. 2 in the first orbital and 8 in the second orbital. Can fluorine do that? Well, absolutely. Fluorine has the highest electronegativity of any element on the periodic table. It very easily pulls in electrons from the outside. So it can very easily pull in an electron from the outside to fill that empty space and give it 8 electrons in the second orbital. So fluorine has an easier way. The nearest noble gas, neon, is right next door. So there we see fluorine, and the yellow arrow is pointing to neon. So if it can just gain 1 electron, it will be like neon. So fluorine can have a full second orbital simply by picking up 1 electron. Now, where might it get that electron from? Well, we'll get into that in our next lesson. But, we'll get into that in this lesson on ionic bonding. And that's what happens, is that fluorine can pick up that electron from lithium. It could pick it up from many other elements as well, but lithium would be a perfect candidate to give up an electron, because lithium easily gives up electrons. Fluorine is very good at pulling them in because of high electronegativity, so it could take an electron away from lithium. That's one way it could do it. So we see that empty space goes away, and we put an electron in there that fluorine has grabbed from somebody, maybe lithium, maybe somebody else, and now you can see fluorine has the electron configuration of neon. 2 electrons in the first orbital and 8 in the second. It doesn't become neon because fluorine still has 9 protons, and that's what defines it as fluorine. So it doesn't become a neon atom. However, it has the electron configuration of neon, meaning its electrons, if you just looked at the electrons alone, they look exactly the way they would look in neon. So conclusion, fluorine gains 1 electron to give it a full second valence orbital with 8 electrons. Alkali metals, alkaline earth metals, or transition metals, boron, by the way, is a metalloid, have low ionization energies and more easily give up electrons. So in general, the metals, which is pretty much everything that's in green with the exception of boron, everything in green there gives up electrons. Nothing that you see in green on that periodic table takes electrons in, ever. Okay, they always give up electrons. So metals always give up electrons. Metals, which can become cations, that is positively charged ions, are shown in the green below. So in other words, when they give up an electron, they lose a negative charge. That means they have more positive charge, protons, than negative charge, electrons, and that's what we call a cation. It's an ion with a positive charge to it. So it has an imbalance of charge in the positive direction, and that's called a cation. More positives than negatives. Nonmetals, and that's over there in the blue, and it could include carbon silicon as well, but definitely those in the blue, have high electronegativity, so they gain electrons. That means they're good at going out and pulling electrons in from other atoms. Nonmetals can most easily complete a valence orbital octet by adding electrons. So nonmetals, which become anions, that is, once they grab an electron or 2, it could be more than 1 or 2, they have a net negative charge. They have more electrons than protons. That gives them a negative charge, and we call a negatively charged ion an anion. and those are shown in the blue. Elements in red can take on either a positive or negative charge, so that's a little more complicated. So we'll avoid talking about those too much initially. We'll talk about really the ones that you see in blue there. Again, the noble gases, those in yellow over on the right, do not want to gain or lose electrons. So even though they're nonmetals technically, we don't count them as nonmetals for the purposes of bonding. The word is inert, and I should have put that on the slide. I-N-E-R-T, inert. It means they really don't want to bond with anybody. They don't want to add electrons. They don't want to lose electrons. Noble gases already have full octets and do not gain or lose electrons. So now we're gonna chug through a bunch of these examples, and the idea of the repetition here is to be sure that this concept is really reinforced in your mind, okay? So first of all, lithium. Lithium can have a complete octet by filling its second orbital. This would require adding 7 electrons. Since lithium has a low electronegativity, that means it doesn't want to pull in electrons from the outside, this would be impossible. It is easier for lithium to give up one of its second orbital electrons, or give up its 1 second orbital electron, as well as the second orbital. This means lithium would have a filled first orbital, the same as helium. So lithium loses 1 electron, giving it a 1+ charge. That's the way we write the charge. It's the number first and then the sign, so it's called a 1+ charge. You can call it a +1 charge, but it's written like that, okay? So lithium now has 1 more. I don't show it in this diagram, I just show nucleus, but it still has 3 protons, only 2 electrons, so it has 1 more positive charge than negative charge, and that gives it a +1 charge. Let's move over to beryllium. Beryllium can have a complete octet by filling its second orbital. This would require adding 6 electrons. So you see beryllium has 2 electrons in the outer orbital. If it added 6 more, it would have 8. Since beryllium has low electronegativity, this would be impossible, same as lithium. Its electronegativity is slightly higher than lithium, but it's still nowhere near large enough to draw electrons in, or to pull in electrons. It is easier for beryllium to give up its 2 second orbital electrons as well as the second orbital. This means beryllium would have a filled first orbital, the same as helium. So it went ahead, it gave up those 2 electrons, which it will easily do. It has a low ionization energy also, just like lithium, and another atom can easily take those 2 electrons away from it. So beryllium loses 2 electrons, giving it a 2+ charge. Boron. Boron can have a complete octet by filling its second orbital. This would require adding 5 electrons. Since boron has a low electronegativity, not as low as lithium or beryllium, but still too low to pull in 5 more electrons, this would be impossible. It's easier for boron to give up its 3 second orbital electrons as well as the second orbital. This means that boron would have a filled first orbital, the same as helium. So boron loses 3 electrons, giving it a 3+ charge. If you could see the protons in the nucleus, boron has an atomic number of 5, so it has 5 protons in the nucleus and only 2 electrons sitting there. So that's a net charge. Net means you subtract the 2. 5 minus 2 is a 3+ charge. It has 3 more positive charges than negative charges. Carbon can fill an orbital by gaining 4 electrons or losing 4 electrons. Generally, carbon does not ionize. Okay, it could go in either direction, but it generally doesn't ionize. Now let's move over to nitrogen. Now we're starting to get further and further to the right side of the periodic table in row 2 here. And we're at nitrogen. So nitrogen can have a complete octet by giving up its electrons as lithium, beryllium, and boron did. This would require nitrogen to lose 5 electrons so that it has a full first orbital identical to helium. So if it lost all 5 of those second orbital electrons, it would be just like the other 3 elements we saw before, would be just like helium. It's easier though, now that we've gotten this far to the right on the periodic table, it's easier for nitrogen to add 3 electrons to give it a filled second orbital. This creates the electron configuration of neon. So if nitrogen just needs to add 3, so instead of losing 5, it's harder for it to lose 5 than it is for it to gain 3, especially since it has a high enough electronegativity to pull in those 3 electrons. We're moving further to the right in the second row. That means the electronegativities of the elements are getting higher and higher. So nitrogen gains 3 electrons, giving it a 3- charge. Again, electrons are negative, so if you add 3 negatives, that's a 3- charge, and now it has the electron configuration of neon. Oxygen can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require oxygen to lose 6 electrons, all 6 of those valence electrons, so that it has a full first orbital identical to helium. But I think you get the idea by now. It's easier for oxygen to add 2 electrons, giving it a filled second orbital. This creates the electron configuration of neon. So we're just going to add 2 electrons to oxygen right there. So now it has the same electron configuration as neon. So oxygen gains 2 electrons, giving it a 2- charge. Again, you add 2 negative charges called electrons, and that gives you a 2- charge. It has 2 more electrons than protons. Fluorine. Fluorine can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require fluorine to lose 7 electrons so that it has a full first orbital identical to helium. While we know that fluorine has a very high ionization energy, nobody's going to take those 7 electrons away from fluorine. That just won't happen. And it also has a high electronegativity, meaning it can easily pull in an electron. So it's much easier for fluorine to gain an electron and be like neon. So it's easier for fluorine to add 1 electron, giving it a filled second orbital. This creates the electron configuration of neon. Fluorine gains 1 electron, giving it a 1- charge. So it's very repetitive what we just did, but the idea is to be sure you understand this concept of how ions work and how the octet rule works, how everybody wants to be like a noble gas, whatever the nearest noble gas is, even if it's the one in the row before it. That might be the nearest noble gas. Okay, so this is a sheet, this is a copy of a sheet that you'll find in your reference sheet section. It's called Common Ionic States of Elements or Charge Numbers of Ions, something like that. Anyway, you can see here that if you look at the first 2 columns, what we just learned is that the first column, the one furthest on the left, lithium, sodium, potassium, hydrogen's kind of an oddball. It really in some ways doesn't belong in the first column. It's not a metal, first of all, but lithium, sodium, potassium, rubidium are. And they lose an electron. That makes them like the nearest noble gas, which is the noble gas in the row before them. So for lithium, that would be helium. For sodium, Na, that would be neon. For potassium, K, that would be argon, and so forth. The nearest noble gas to each of those is the one in the row before it. So it goes backwards, in other words. The same is true of the second column. Those are the alkaline earth metals, and that would be beryllium, magnesium, Mg, calcium, Ca. They lose 2 electrons to be like the nearest noble gas, which is the one in the row before them. So beryllium would give up 2 electrons, it would lose its second orbital, and it would have an electron configuration like helium. Magnesium would give up 2 electrons, it would then lose its second orbital, it would only have a first orbital, and then it would, I take that back. Magnesium would give up 2 electrons, it would lose its third orbital, and that would give it only 2 orbitals, and it would have the electron configuration of neon in the row before it. It goes backwards, in other words. That's the closest noble gas. Calcium has 4 orbitals, and the valence orbital has 2 electrons, so it gives up those 2 electrons. Now it only has 3 orbitals. All of them are filled, so it looks exactly like the electron configuration. It looks exactly like argon, the noble gas that's 2 places before calcium in the row before it. And so that's how those work. Now if we go over to the column where boron is, that's a +3. Boron more easily gives up 3 electrons, as we talked about. It's easier for boron to give up 3 electrons and be like helium than it is to gain 5 electrons and be like neon. So everything in that column with boron becomes a +3. Aluminum, gallium, indium, and so forth, they all give up electrons to be like the noble gas that's in the row before them. All right, now we get to the carbon, and we said carbon is doesn't ionize. Those in the middle could go either way. They could add 4 or lose 4, but they tend to not do either. And so they really don't ionize. Now we move over to the -3 column. That's nitrogen, phosphorus, arsenic, and antimony. And those are closer to the noble gas on the left of them at the end of their row. So each of those would gain 3 electrons and have a full octet, and that would make nitrogen like neon. It would make phosphorus P like argon. It would make arsenic like krypton, and so forth. They would add electrons, so that gives them a 3- charge or a -3 charge. Oxygen, sulfur, selenium, tellurium, those would each gain 2 electrons to be like the noble gas that's at the end of their row. So oxygen would be like neon, sulfur would be like argon, selenium would be like krypton. And finally the halogens, that's the second to last column, fluorine, chlorine, bromine, iodine, would each gain 1 electron to be just like the noble gas that's closest to them, which is right next door. If they gain 1 electron, they'll be just like the noble gases at the end of their rows. Okay, now those aren't too bad, and you can figure those out. It's the ones in the middle that you can't memorize, and those are the transition metals. And if you look at them, you'll notice many of the transition metals have more than one possible charge. So while you can figure out the charges on the first 2 columns and the last 6 columns, as we just did, the ones in the middle where the transition, the valley, what I call the valley in the middle where it's low there, you notice that most of those have more than one possible charge. And if you look at Fe, iron, number 26, right in the middle on the 4th row, it has a 2+ and a 3+. It actually has about 6 or 7 different charge numbers that it can take on. But they're only showing the more common ones. In that case, it's a +2 or +3. What that means is iron can either lose 2 electrons and become have 2 more protons than electrons, +2 charge, or it can lose 3 electrons and have 3 more protons than electrons, and that would be a +3 charge. Some of the others that you'll commonly see are copper. Copper is a 1+ or a 2+. Down below it is silver. Silver only has a single charge. That's a 1+. Down below that is gold. Gold can have a 1+ or a 3+. Gold is Au. And again, those are the ones you'll see, some of the more frequent ones that you'll see, but it could be any of those. So that's why you need this particular periodic table. You can't memorize the transition metal charges. There's too many of them, and you're not expected to know them by memory, okay? But you should be able to figure out the ones we just said in the first 2 columns and the last 6 columns just by looking at where they are on the periodic table and figuring out how many electrons they're either going to gain or lose. So here's a couple of examples. Iron can lose either 2 or 3 electrons, giving it a 2+ or 3+ charge. Copper can lose either 1 or 2 electrons, giving it a 1+ or 2+ charge. Tin can lose either 2 or 4 electrons, giving it a 2+ or 4+ charge. Lead, Pb, can lose either 2 or 4 electrons, giving it a 2+ or 4+ charge. Okay, now this is just kind of a reproduction of another sheet you have in your reference sheets. It's called the 60 Common Ions, and I'm just going to go over this with you a little bit. It has 4 sections to it. The one at the top are the most basic ones. Those are the ones that, for the most part, you should be able to figure out by looking at the periodic table what their charges would be. For example, potassium or sodium are +1. Iodine is a -1 because it's a halogen, and so forth. Oxygen is a 2-, and so forth. The next group down, the second group on that, is those transition metals that I was talking about just a minute ago. And so you'll notice, for example, that tin has a 2+ or a 4+. Iron has either a 2+ or a 3+, and so on. Copper has a 1+ or a 2+, and so on. So those are the transition metals. Down below are some of the molecular ions, which are ions that are formed by covalent bonds, which we haven't talked about yet, but I'm just pointing it out. I didn't show it here, but we'll go over that sheet in class sometime to be sure you know how to read it and how to find the different ions. So the two sheets that you can use for this are this sheet right here, which is in your reference sheet section. The advantage of this sheet is it has every single element on the periodic table. The 60 common ions does not. However, those molecular compounds that form ions are not on the last sheet. They're only on this sheet. Again, you're not seeing them right here on the screen now, but when we go over that sheet, you'll see them. So both sheets have their place where you can use them, but they both have serve the same function, is to help you identify ions. Okay, now that we've talked all about ions, we're going to talk about ionic bonds. It's one of the three main ways that compounds form bonds, that elements form bonds with each other to form new chemical substances, new chemical compounds. So an ionic bond, here's this, I'm going to kind of explain this in about 3 or 4 different ways using animations, and hopefully one of them kind of sticks in your mind, maybe more than one of them kind of sticks in your mind. But this first one is the very simplest. So lithium has an electron. As you know, it has 2 inner electrons, core electrons in the first orbital. It has that 1 electron sitting out there in the second orbital, and that's represented by the electron you see there. Fluorine has 7 electrons in its valence orbital, but it has an open spot to take in a new electron. As we know, lithium has a low ionization energy, so it easily gives up an electron. Fluorine has a high electronegativity, so it pulls in an electron. So if you watch the animation here, that electron flies over from lithium to fluorine. So ionic bonds result when an atom transfers an electron to another atom. The atom that lost the electron becomes a positively charged cation, and the atom that gained the electron becomes a negatively charged anion. Positive and negative charged atoms attract each other and form ionic bonds. Like that. That's in the simplest sense what an ionic bond is. There's really no more complicated than that. They basically create a positive and negative charge with each other by passing an electron, and then the positive and negative charge, as we know, positive and negative charges attract each other, and so those 2 atoms come together and they stick. And that's what's called an ionic bond, because it's formed from 2 ions, 1 anion and 1 cation. Ionic bonds must be electrically neutral, so these 2 are. One has a +1 charge, one has a -1 charge, and so that's electrically neutral. They balance out. Ionic bonds create a cubic structure called crystal lattice structure. The smallest unit of a crystal lattice structure is called a unit cell or formula unit. Lithium fluoride, which is what you see here, is an example of a formula unit. So let's look at that. Cube up there. What you notice is that they're kind of stacked like bricks, and you'll notice that, for example, there's a purple one in the middle right here where I'm circling my cursor. Now, that purple one would be a lithium, and the green ones would be fluorines or fluorides, and we're going to talk about naming. Why is it called fluoride rather than fluorine? We'll talk about that in a later lesson, but it's called lithium fluoride when it bonds. That's one of these green ones. But the question is, if it's 1 lithium for 1 fluorine, which fluorine does this lithium belong to? Does it belong to the one on the right, the one on the top, the one on the left, or the one on the bottom? Or there's actually one behind it inside that you can't see very well, or you can barely see it? Which one does it belong to? And the answer is, it doesn't belong to any one of those. So it's not as though this lithium belongs to just this fluorine. It kind of belongs to all of the fluorines around it. The same is true of the fluorines. If you look at this one on the bottom right here in the center, Which lithium does it belong to? Well, it belongs to the one on the left, it belongs to the one on top, it belongs to the one on the right. So they kind of are shared. It's kind of like a community. It doesn't belong to any one lithium, but what there is a one-to-one relationship. For every lithium in this cube, there's one fluorine. And so that's called a formula unit. It's the smallest unit of this cube. It's a one-to-one relationship of one lithium to one fluorine, and that's called a formula unit. Okay, so that's and the structure as a whole is called a crystal lattice structure. Okay, the atoms that give up electrons are usually alkali metals, alkaline earth metals, or transition metals. These elements have low ionization energies, so they can easily give up electrons. So everything that got covered in green, those are the alkali and alkaline earth metals, and these are the transition metals. So those are the ones that give up electrons. They become cations, they become positively charged. Metals never become anions, they never take in electrons. The atoms that attract electrons are usually nonmetals, particularly halogens. That would be fluorine, chlorine, bromine, the ones second column from the end. These elements have high electronegativity, so they strongly attract electrons. When lithium and fluorine get together, lithium gives up one of its valence electrons to fluorine. Lithium has low ionization energy, which means it easily gives up its second orbital electron. Fluorine has high electronegativity, so it wants to pull in an electron. So they match up very well for that purpose. Fluorine will pull on the electron of lithium, and lithium will give it up. So the animation, it looks like this. And that electron flies over there. And now that second orbital in lithium goes away. And so now lithium has a full valence orbital. Its first orbital has 2 electrons. That makes it full. And fluorine has a full valence orbital. Its second orbital has 8 electrons, and that makes it full. So everybody's fulfilled the octet rule. Everybody's happy. In addition, lithium now has a positive charge, and fluorine now has a negative charge, which means that they're going to attract each other. So the negative charge and the positive charge are attracted to each other to form a bond. This is an ionic bond because it is formed by 2 ions. Lithium is a positively charged cation, positive cat, remember the smiling cat, because it has 1 more proton than electron. Fluorine is a negatively charged anion, negative ant, because it has 1 more electron than proton. Notice that ionic bonds follow the octet rule. Lithium's valence orbital, which is now its first orbital, is full. Fluorine's valence orbital is also full. So both are at their most energetically favorable state. They want to have full octets. That makes them what's called energetically favorable, the lowest energy state that they can be in. Okay, let's look at the explanation again. In ionic bonding, alkali, alkaline earth, or transition metals, those are weak guys. So you can just think of the metaphor, they're weak guys. They send an electron over to nonmetals, the strong guys. This makes the alkali, alkaline earth positive, or it could be a transition metal, and the nonmetal negative, so that they attract each other. So these guys become positively charged because they've lost an electron or more, or 2 electrons. These guys become negatively charged because they gained an electron, and there goes the electron. It passes over to there, and so the nonmetals have a negative charge, they're anions. The metals, the alkaline earth metals, have a positive charge because they've lost an electron or 2 electrons, and so positive negative attracts each other. Let's look at it again in another way. Ionic bonds happen between a metal and a nonmetal. The high electronegativity of a nonmetal pulls on the electron of a metal. So the strong guy is pulling on the electron of the weak guy. The low ionization energy of a metal means that it easily gives up electrons. The electron is passed across the periodic table from left to right. The metal, the weak guy, loses an electron and becomes a positive cation. You see the positive cation above the weak guy over there. The nonmetal, strong guy, gains an electron and becomes a negative anion. So you see negative anion above the strong guy over there. The cation and anion become friends and are attracted to each other to form an ionic bond. Okay, it's just that simple. That's how an ionic bond happens. Again, they have to be electrically neutral. Once they get together like that, the positive, negative balance each other out, and an ionic bond is always electrically neutral. It's formed from two ions, but once they put together, it has to be electrically neutral. So using the charge numbers of ions or 60 common ion sheet, assign a charge number to the ion. So remember, they have to end up electrically neutral. So use the crossing arrow method to assign the subscripts. Remove any that should be minus signs. Reduce the subscripts if they have a common factor. So I'll give you some of these to practice on the assignment. So let's look at these two. Na and Br. So you should have a periodic table in front of you, or the charge numbers of ions, or the 60 common ions. And if you did, you would see that Na likes to lose an electron to be like the nearest noble gas, one row behind it, and bromine likes to gain an electron to be like the nearest noble gas in its row. And so Na will become a 1 plus, and bromine will become a 1 minus. So what you do to form the subscripts of this compound is you simply take the 1 minus from bromine and put it down underneath Na, take off the minus sign, and take the 1 plus from Na and put it down beneath the bromine. That's 1. So that would be Na1 Br1, but you don't write ones, just like in math class. If you have a coefficient or exponent of 1, you don't write it. So that's really Na1. There's 1 sodium for every 1 bromine. So 1 plus charge balanced with 1 minus charge. They attracted each other just like lithium fluoride in the previous slides, and they attract to form an ionic bond. How about potassium and oxygen? So again, if you look at your periodic table, you don't even need the periodic table of charges. You should be able to look at these two elements as you practice this and tell what the charge will be. Potassium is the first element, is in the first column rather, so it's going to give up 1 electron to be like the nearest noble gas. And oxygen is the second column from the end of the periodic table, so if it gains 2 electrons, it's going to be like neon. It's going to be like its nearest noble gas. So potassium likes to take on a 1 plus charge. It likes to give up 1 electron, and oxygen likes to take in 2 electrons. But there's a problem. That doesn't balance. So simply the way you solve that is you use 2 potassiums. So if you have 2 potassiums and each one gives up 1 electron, and the oxygen likes to take in 2 electrons, then that would be the 2 potassiums giving up 2 electrons and the 1 oxygen taking in 2 electrons. So what you would do is you would crisscross those numbers. So the 2 on the oxygen goes down underneath the K, and the 1 on the K goes down underneath the O. We don't write it though, so it's K2O. So that's electrically balanced. You have 2 positive charges on the K, 2 negative charges on the 1 oxygen, so the 2 plus, 2 minus balance out. They attract each other and they form an ionic bond. Okay, beryllium and selenium. So beryllium wants to form a 2 plus charge. If you look at it, it's in the second column on the periodic table. It likes to give up 2 electrons to become like the noble gas in the row before it. Selenium likes to take on 2 electrons because it's in the second to last column, or actually third to last column from the noble gases. So it likes to take on 2 electrons to become like the nearest noble gas. So what that would do is that would give you Be2, you crisscross the 2's, Se2. But since they have a common factor there, it's just like math, you could factor out the 2. If there's 2 berylliums for 2 seleniums, then that means there's 1 beryllium for 1 selenium. So you write it in the lowest terms, And so that would be BeSe. You don't write Be2Se2, you write Be1Se1 or just BeSe. Okay, how about iron and nitrogen? Well, first of all, you have to decide what kind of iron it is. Is it iron 2 or iron 3? Well, let's say it's iron 2. If it was iron 3, it would be easy because iron 3 would be 3+. That would match up perfectly with nitrogen 3-. So 3 plus 3 minus would match up perfectly. That would be a 1-to-1 relationship. If it's 3 irons to 3 plus iron to 3 plus nitrogen, it would just require 1 iron to match up with 1 nitrogen. It would be a perfect mix. But I decided to make it harder. Let's make it Fe2, the 2 plus version of iron. Remember, it could be either 2 plus or 3 plus. So you have a 2 plus for iron and a 3 minus for nitrogen. So you simply crisscross the numbers, take off the signs and crisscross the numbers. So it becomes Fe3N2. All right, so if you have 3 2 plus irons, 3 times 2 plus gives you 6 plus. If you have 2 3 minus nitrogens, 2 times 3 minus gives you 6 minus. So you have 6 plus, 6 minus, that balances perfectly. So Fe3N2 would be electrically neutral, it would balance. All right, so you've learned about one of the 3 major type of chemical bonds called an ionic bond. I really want you to have this explanation memorized. The memorization is secondary to just understanding it. But be sure you understand why it works, how to determine if I gave you a couple of elements, one that was a metal and one that was a non-metal, could you figure out what the ionic bond would be and what the subscripts, what we did on that last slide, would be for that. And we'll practice that on the assignment, so you'll get plenty of chance to practice that, okay? So that takes care of that. So we'll see you in class next time, and we'll see you then.